Second day, section 5.6, and we're going to do some more work with inverse trig functions today. So first goal, we're going to solve some equations. So problem number 1 is our first goal, and then problems 2 through the end, we're going to be taking derivatives of equations that have inverse trig functions in them. So a bit of a challenge here. We're going to try to create a little bit of space. So this first one, now I'm going to solve this equation. If I go to solve this equation, what have I got going here? So arc sine of root of 6x is the same as arc cosine of root of 2x. Well, you know what I'm going to do? I'm going to get rid of one of those inverses. Whichever one you want, doesn't matter. How about if we do this? How about if I say, instead of having arc cosine on this side, how about if I put a cosine over here on the left? And again, remember our goal. If we can come up with a quadrant and a reference angle, we're golden. So let's start with that theta substitution that we worked on earlier in 5.6. So if I do that, what I'm really looking for now is I have this equation. Cosine of the quantity theta is the same thing as root of 2x. That's what I'm working toward. Now if I could just come up with what the cosine of theta is, I could, in terms of x, if I could come up with a cosine of theta in terms of x, I could set it equal to root of 2x, and I'd be golden. So that's our challenge right now. Can we come up with what the cosine of theta is? So I'm going to take this theta equation that I have over here, because we said theta is the same thing as arc sine of root of the quantity 6x. So that means what I really know is the sine of theta is the root of 6x. And oh, that looks like something I could make a triangle out of. So here's my theta that I'm working with, and according to that, my opposite side is going to be the root of 6x, and my hypotenuse is going to be 1. So in order to come up with this third side, let's see, I'd be doing a little, let's see, 1 squared is 1 minus root of 6x quantity squared, and then I'd put all of that underneath a square root, and that would give me my third side. So it looks like square root of 1 minus 6x for my third side. So that's there's my value. Now what are we looking at? We're looking at the cosine of that thing. So cosine would be that root of 1 minus 6x, that's the adjacent side, divided by the hypotenuse, which is 1, and we're going to set that equal to root of 2x. Well, now I've got an equation that looks like I can solve. So if we want to solve that equation, how about if we square both sides? If I square both sides, left side looks like 1 minus 6x, right side looks like 2x. Add your 6x over to the other side. So 1 is the same thing as 8x. Looks like my x is going to end up to be 1/8. And if I wanted to check real quick whether or not that solution worked, if we went back over 1/8, like if we came back up to this square root and put 1/8 into it, I think that would be fine. We'd end up 1 minus 3/4. We'd end up with positive values. So that's inside the root. So that's a good thing. So there's your solving of a trig function. Now, that's goal number 1. Goal 2, differentiate equations that have inverse trig functions in them. So now we're going to try to work on taking derivatives. Well, I would imagine right now you're anticipating that, oh, I know how these rules usually work with regular trig stuff, and I have trouble with those derivatives. I have trouble with those anti-derivatives. I think you're going to like this a little bit better. And the reason I think you're going to like this better is because we're going to treat it a lot the same way that we did before. And I'm going to start with this problem. Instead of calling this thing f of x, I'm going to start with a y right there. And if I did that and I said to you, what do we really want to know? A lot of you guys would start off by rewriting this equation and say, well, I want the secant of y. I want to know what angle has a secant that's equal to 4x. Okay, well, is that equation, think back to your days in chapter 2. That's an equation we know how to take the derivative of. Derivative of secant of y. Okay, derivative of secant y. Secant y, tangent y would be the derivative of secant. Derivative of y would be dy over dx, and the derivative of the right side would just be a 4. Well, so your challenge now is, can you write secant of y and tangent y in terms of x? Because if you can, you're golden. Well, how would we do that? Why would we do that? Well, we do that because we're trying to find dy dx. We introduce this y in here. We want to write this thing find this derivative with respect to the given variable. Our variable is x. We want to write everything in terms of x. Standardized test answers are all going to be in terms of x in a problem like this. So need is a reference triangle. Secant of y. Secant is 4x, so that means my hypotenuse is 4x, my adjacent is 1, my third side, square root of 16x squared minus 1. There's my triangle. Can we express the secant and the tangent of that y? Well, the secant of y we already know. That was given us to be 4x over 1. The tangent of y, well, tangent would be that root of 16 minus x, or 16x squared minus 1. I better write this so we can read it. Over the top of a 1 times my dy over my dx is equal to my 4. Well, so solve for your dy dx. What's dy dx going to look like? My dy over my dx, divide by 4x, divide by 16x squared minus 1 underneath the square root. Clean it up. My derivative, 1 over x times the root of the quantity, 16x squared minus 1. Now, is that a little bit involved? Yes, but as far as difficulty level, think about what you had to do. You had to rewrite an inverse trig function into an equation. That equation is one you know how to do the derivative of. You took the derivative, and then you used what you know about inverse trig functions to make your reference triangle and to replace. That's all you had to do. So what's new about this? Not very much. In fact, very little. So the key is still that reference triangle, and once you can get to that reference triangle, you're in good shape. All right, number 3. The first thing I need to make sure that I illustrate for everybody is you have two things being multiplied together here. And if you're going to find the derivative of it, you're going to need product rule. So product rule. My derivative, let's see, x times whatever the derivative of arctangent of x is, plus arctangent of x being multiplied by the derivative of x, which is 1. So there's my derivative. If I could only just fill in whatever the derivative of arctangent of x is, well, I think you probably know where I'm headed. Theta substitution. Tangent of theta, what do we know? Tangent of theta is equal to my x, right? If arctangent of theta is equal to x, then tangent of theta is equal to x. What's the derivative of tangent theta? I need the derivative of theta now with respect to x. This would be d theta over dx going right there, the derivative of that second expression. So all I have to do is come up with what d theta dx is. So tangent of theta, derivative of tangent of theta would be secant squared of theta times d theta over dx. And the derivative of x is going to be 1. So what I have is d theta over dx is 1 over the, so divide both sides by secant squared. If you divide by secant squared, that's the same as multiplying by cosine squared of my theta. Now the only trick is my original problem didn't have any thetas in it. It had all x's. So what I'd really like to do is I'd like to represent d theta dx using x's. So if I need to do that, let's see, I'm probably going to need a reference triangle. Where will I get my reference triangle from? How about right here? Reference triangle. Tangent of theta is x. x, 1, hypotenuse would be the square root of 1 plus x squared. So I know what all my sides are. So now if that's the case, then the cosine of x that we're going to square would be 1 over the square root of 1 plus x squared. And we're going to square that thing. So if I really want to know what the cosine of theta is, I'm looking at 1 over 1 plus x squared. Bring this back over. That is your d theta dx. So we're going to put 1 over 1 plus x squared inside that bracket. We're going to multiply it. Whoops. We're going to multiply it by an x, and we're going to add to it an arctangent of x. And that's going to be your dy over your dx. So wow, how did we get there? We started with a product rule. There was something we didn't know. We represented what we didn't know using a triangle. We took the derivative, used our reference triangle to rewrite that derivative in terms of the x's that we were originally given, and we plugged everything back in. All right, 4 and 5. So number 4, here we are again. I'm thinking, as soon as I see that now, this is starting to become my habit. I've got sine of arc cosine of t. I'm going to make arc cosine of t be my theta. So what I really have, rewriting my equation, h of t is really the sine of theta. So if I wanted my derivative, my h prime of t, derivative of sine of theta would be cosine of theta. Derivative of theta would be d theta, and we're taking the derivative with respect to t. So that was an implicit differentiation problem with a pink theta inside of a black sine. Now all I have to do is I have to find a way to represent the cosine of theta and d theta dt in terms of the t that was originally given to me. So let's do this thing with this theta again. So according to this statement right here, the cosine of theta would be the same thing as t. Well, that's nice. So I know right now I could put a t right here, but representing what's going to happen with the rest of it is going to be the question. So let's see. So cosine theta, derivative of cosine theta would be the opposite of sine of theta times d theta dt, and that would be equal to a 1. So my d theta dt would be 1 over sine of theta, negative 1 over sine of theta. All I have to do now is come up with what that means. So I need something to represent those values. So I need a reference triangle. Where's my reference triangle going to come from? My reference triangle is going to come from this statement right here. Cosine of theta is equal to t. So if cosine of my theta is equal to t, then my adjacent is t, my hypotenuse is 1, my other side is be 1 minus t squared underneath the square root. So I want 1 over the sine, and I want to throw a negative sign on it. So it looks like, let's see, the sine would be the root of 1 minus t squared over 1. We want to put that, well, let's write it so it looks like it's supposed to. Negative 1 over the quantity root of 1 squared. And then it's divided by 1, I guess, technically. Sorry about writing this so that we can't read it. Let's write it so it's legible. Square root of 1 minus t squared. So there is my d theta dt. Now take that d theta dt, bring it back up here to your original equation. And just like that, we have rewritten our derivative. Okay, so the key to all this is that theta substitution and being able to represent your trig function with a right triangle. All right, last one. So this time, I'm hoping that you're starting to recognize this right now. Let's call this thing theta. What do we really have? We really have f of x is equal to 2 thetas. So if we go to take our derivative, our f prime of x is a nice easy one. Would be 2 times the derivative of theta, which would be d theta dx. We took the derivative of that equation with respect to x. So all we got to do is represent that stuff. So if we go to represent that stuff, let's see. So looks like according to this thing, the sine of theta is the same thing as x minus 1. So a nice little derivative, cosine theta d theta dx would be equal to 1. So my d theta dx that I'm looking to plug into the problem, divide by the cosine 1 over the cosine of theta, or if you wanted to think of it that way, that'd be the secant of theta. Either way would work fine. We need a reference triangle. That's going to come from right here, reference triangle. This one might get a little bit tricky because our theta that we have, the opposite would be x minus 1. The hypotenuse would be 1. Finding this third side is going to be a little bit of a trick. So how about square root of 1 squared minus the quantity x minus 1 squared. You could leave it like that. If you wanted to, you clean it up and go a little bit further, but that's really what this third side is. So I'm just going to leave it in that form because there's really nothing wrong with it. So what's my f prime of x? My f prime of x would be 2 multiplied by, oh sorry, I haven't done d theta dx yet. Kind of missing that. So now my d theta dx, what's that going to look like? 1 over the cosine, which would end up being 1 over that square root divided by 1. Well, that square root is 1 minus the quantity x minus 1 squared. So there's my d theta dx. Now bring this back over, and I kind of got a little ahead of myself a second ago. So it looks like I've got 2 times 1 over that square root, which is going to end up putting that same square root, 1 minus x minus 1 squared, in our denominator. So are there places to make mistakes? Yes. Is the process especially difficult? I don't believe so in my opinion. But you just kind of have to look at what do I have, what do I need, and see if you can represent it. So that's inverse trig derivatives.